Welcome back. In this session, the second part of Set 4 will tackle another fundamental data type, rational numbers or fractions. This problem provides an excellent opportunity to deepen our understanding of creating custom classes, managing their internal state, and especially leveraging the power of operator overloading to make working with our fraction objects feel natural and intuitive. Problem 1 asks us to create a class called rational to perform arithmetic with fractions. The core data are the numerator and denominator, which should be int variables and kept private. Encapsulation. Using private instance variables is fundamental encapsulation, hiding the internal representation of the fraction. We need constructors, a parameterized one, int numerator and int denominator, and a parameterless one with default values like 0/1. Constructors ensure our rational objects are properly initialized when created. A crucial requirement here is that the constructor should store the fraction in reduced form. For example, 2/4 should be stored as 1/2, data integrity invariance. Reducing the fraction upon creation helps maintain data integrity. Every rational object internally represents the simplest form of that fraction. We need to perform standard fraction arithmetic, add, subtract, multiply, divide. All calculation results must also be in reduced form. Display is required in a over-B format and also in floating point format, potentially with specified precision. Bonus comparison operators like less, less, or equal, greater, greater, or equal are mentioned. Declare overloaded operators plus, minus, slash, star, and divide that replace the class's methods for adding, subtracting, multiplying, and dividing fractions. Test your new overloaded operators. Operator overloading, polymorphism. This is the core focus. Instead of methods like add, rational other, we will use the plus symbol directly with rational objects. This is polymorphism, giving the plus operator new behavior for our custom type. Let's look at the solution code, fields, the private int numerator and private int denominator fields implementing the encapsulation requirement. Constructors. The parameterized constructor takes num and denom and assigns them directly. The parameterless constructor should use constructor chaining, this 0, 1, to call the parameterized one with default values. Operator overloading plus. We see public static rational operator plus, rational R1, rational R2. Operator overloading polymorphism. This is our first overloaded operator for rational numbers. It defines how the plus operator works with two rational operands. It's a static method that takes R1 and R2 and returns a new rational object representing their sum. The code inside implements the standard fraction addition formula. This allows us to write R1 plus R2 directly in our test code. Operator minus, public static rational operator minus, rational R1, rational R2. This overloads the subtraction operator, implementing the standard fraction subtraction logic. Star operator. This overloads the multiplication operator using the simple fraction multiplication formula. Note on reduction after operation. Similar to the constructor, the problem required that all calculation results be in reduced form. This overloads the division operator. It implements the multiply by the reciprocal rule for fractions. Edge case handling. A check if R2.numerator equals 0 to prevent division by 0, throwing an exception, making the operator robust. Comparison operators. We define how less, less or equal, greater, greater or equal work with rational objects. The implementation simplifies the comparison by casting the fractions to double and comparing the resulting floating point values. ToString method. This overrides the base object class's ToString method to provide a custom formatted string representation of the fraction a over b, including handling the cases where the fraction is 0 or a whole number. To double two formatted string methods. Provide methods to get the floating point representation, including specifying precision. Slide 8 shows the main method testing the rational class from part 1. Problem 2 introduces an enhanced version of the rational class. The structure changes slightly to include a whole number field in addition to the numerator and denominator. Data validation. A key requirement for the denominator's set accessor is validation. It must not allow a 0 value. It should default to 1 if 0 is attempted. This enforces data integrity at the point of modification. We need 3 specific constructors, one taking whole number, numerator, and denominator, one taking only numerator and denominator. Whole number defaults to 0. and a parameterless one, whole number and numerator default to 0, denominator to 1, constructors and chaining. Multiple constructors provide flexible object creation, and we'll see constructor chaining used here. Importantly, the problem states that rationals do not have to be reduced to proper form after construction in this version. However, it requires a separate reduce method that can be called to reduce a rational to its simplest and proper form. Abstraction: the reduce method encapsulates the complex logic for simplification. Let's look at the solution code for the enhanced rational class in Part 2, Constructors, 3 required constructors. Notice the use of constructor chaining, this 0ND and this 001, denominator property with validation. Emphasis on encapsulation and data validation. The set accessor explicitly checks if value not equals 0. If the value is 0, it prints a message and sets the denominator to 1, otherwise it sets it to the provided value. This is a clear example of using a property setter to validate input and maintain the object's integrity, preventing a 0 denominator which would represent an invalid fraction. This slide shows the re-implementation of the overloaded plus and minus operators for the enhanced rational class. Calculation logic, improper fractions. The code first converts both rational objects to their improper fraction form. It then performs the standard improper fraction addition, reduction after operation, create a new rational from the result, and then call new rational.reduce. This ensures that the result of the addition is always returned in its simplest, proper, or improper form, fulfilling the requirement for reduced results. Operator minus. This overloads the subtraction operator, following a similar pattern, convert to improper fractions, subtract, create a new rational, and call reduce. This slide shows the multiplication and division operators for the enhanced rational class, star, operator. Overloading the multiplication operator. It converts to improper fractions, multiplies numerators and denominators, creates a new rational, and calls reduce. Operator division. Overloading the division operator. It converts to improper fractions, checks for division by 0, multiplies by the reciprocal, creates a new rational, and calls reduce. Data integrity, negative denominators, include logic to ensure the denominator is not negative after the calculation by negating both numerator and denominator if needed. This helps maintain a consistent representation. These overloaded operators are more complex than in Part 1 because they handle the whole number part. This slide shows the public void reduce method, abstraction. This method encapsulates the entire logic for simplifying a fraction and converting improper fractions to mixed numbers. This complexity is hidden within this method. The overloaded operators just call reduce. The method handles negative signs, converts improper fractions to mixed numbers by updating whole num and numerator, and then uses a helper GCD method to find the greatest common divisor to simplify the remaining fraction part. The GCD method is marked private, further hiding internal implementation details. ToString method, implement override string toString. It now handles displaying the fraction in different formats based on the whole num and numerator values, just 0, just the whole number, just the fraction part, or the mixed number format. A 2-decimal string method. This method calculates the floating point value and formats it to a specified precision with a default value of 2. These slides show various test programs demonstrating the enhanced rational class. Mixed number operations. Slide shows tests with a rational number that has a whole number part. Complex usage with arrays. Slide shows a more complex demo using an array of rational objects. The loops demonstrate performing addition and multiplication between all pairs of rationals in the array using the overloaded operators. This extensive rational numbers problem provided excellent practice with core OOP principles and put a strong emphasis on operator overloading. We saw how to design a class, manage internal state with fields and properties, including validation, create objects with constructors and chaining, encapsulate complex logic in methods like reduce and GCD, and crucially, use operator overloading to define intuitive arithmetic, comparison, and even increment-decrement behaviors for our custom rational type. Operator overloading makes our classes feel more integrated with the C# language and easier to use in calculations. Thank you for joining me for this session.